Okay, so that's the plan. And the plan in the second thing is first I do sort of a generic thing on Bogoliubov transformations. Then I'll do the specific Bogoliubov transformations for unroof or accelerated frames, and then that segues into 2 or 3 different treatments for Hawking, depending on how much time I get.
Okay, now I can see everything.
All right. So with that, so here for scale symmetry, most of the time, many times, theories don't have dimensionful scales, or even if they do, they can be taken to be small. So QCD with light quarks is an example. And so let's just look at some of the consequences of this. So if you don't have masses in the Lagrangian, you have no fixed scale. We can turn that into a symmetry by just doing some rescaling. So let's take x is of lambda x prime, d4x is lambda to the 4th, d4x prime. So there I'm rescaling coordinates. D mu is 1 over lambda d prime mu. But I can also then rescale fields. Let's take fields d mu of x and call that lambda to the minus 1, a mu of lambda x prime. So I'm going to change my, and this is I'm going to change field variables. And so f mu nu goes to 1 over lambda squared f mu nu of lambda of x prime. One of the derivatives, one of the lambdas comes from the derivative, one comes from f. Okay. For fermions, the transformation is psi of x, lambda to the minus 3 halves, psi of lambda x prime. And so if you have something like QED or QCD, you have an action which is the integral d4x minus a quarter f nu, plus, let's take a generic fermion. Then this turns into d4x prime lambda to the 4th times minus 1 over a quarter, 1 over lambda to the 4th f mu squared, and then plus 1 over lambda to the 4th psi bar I d slash psi. And then the last piece, the m piece, looks like it's minus m 1 over lambda cubed psi bar psi. Okay, so the rescaling f squared is invariant, psi bar d slash psi is invariant, but the mass term breaks the invariance.
So let me show you guys something.
So associated with that should then be another current. Okay, so there should be a current associated with that.
All right. So.
And that current should be conserved if the mass is 0. Okay, so the general structure of this is that this current, this scale current, is something like theta mu nu x nu minus some other current J called the virial current. Okay.
Function does, it takes a number, right, and spits out another number.
So if you just constructed, let me just start a construction. I'll do partial construction. Okay. Actually, the thing I have worked out here is a scalar, where a scalar transforms as phi of x is lambda minus 1 phi of lambda x. Remember, when you do Noether's current, you would let the parameter depend on position. So I'll let lambda equals 1 plus, let's call it eta of x. And I'm going to look at the variation with respect to d mu eta. Okay. So if I do this, I have phi of lambda x is phi of x plus eta of x d mu phi of x. Okay, guys, there's a good deal of noise coming up from there. I'm not sure what's going on in the background, but
Internet. Oh.
Okay, thank you. So when in the Lagrangian one, I have d mu phi, that turns it into d mu phi plus things that just involve eta, plus then there's a d mu eta times phi piece. This is the piece that's going to start generating the current, and actually I blew it. I blew it. Okay, there's actually an x here. Okay, let's just say this again here. This is phi of 1 plus eta x. So when I'm Taylor expanding it, the small parameter is eta times x. So it's eta times x times the derivatives. Okay, sorry for that, because that's the important piece. That was the piece I was trying to illustrate. And then so there's an x, let me call it x sigma d sigma phi here, just to keep the indices separate. So there's a derivative on eta x sigma d sigma phi. The Lagrangian then has, remember the Lagrangian was d mu phi, d mu phi. I have rushed way too much. Let me back up. So let's go back to this line here. Sorry. I'm looking here actually at d mu lambda to minus 1 phi of lambda phi. That's d mu 1 minus eta phi plus eta, let's call it x sigma d sigma phi. So now when I take the derivative, I get both pieces. I get when I'm taking the variation of this Lagrangian, I get terms that are like before. I get a d mu eta with phi from that piece there, from taking the derivative there, and then another one from here, which is eta, d mu eta x sigma d sigma phi. Okay, and this is multiplied by 2 d mu phi. So what I'm after here is after showing you, here's where the x sigma times things that look like the energy momentum tensor come, and here's where the virial current comes. It's a d mu phi phi. So here the scale current is theta mu nu x nu, and then this scale current is phi d mu phi. Okay. If I've got my constants right, I'm only worried about a factor of 2, but I think that's the correct one. If you take the usual energy momentum tensor for a scalar, and you take its divergence, this guy cancels this. And so the divergence of J mu scale, well, the divergence of theta is 0, so it's theta mu mu. So I just take the derivative of x minus it's d mu phi from the second piece there. And if I've got my factors of 2 right, that should be 0. Okay, so I do get a symmetry. The equivalent one for the photon, which is the one I'm going to be working on here, is if we just do this unchanged, yeah, so theta mu nu for the scalar field, is d mu phi d nu phi, and then there's a minus g mu nu d mu phi d lambda phi d lambda phi, and that comes with over 2. Okay, so the piece actually we got out here was we got this piece here is the x times that term. Okay, this one actually comes from varying the Jacobian in the action. Okay, so I didn't do the full derivation of this for you, but I just wanted to show why the x appears there. It comes from this Taylor expansion of the field variables. If we do this for E and M, for the photon, the another current, the scale current, is theta mu nu x nu again minus f mu alpha a alpha, where this theta is the canonical or another current, which I remember we constructed early in the class. At the very start of the class, we did this. This guy is not symmetric. Okay. But then we showed that there was this ambiguity in theta mu nu, where you could add total derivatives, and we converted this to a symmetric, which we called T mu nu, which is minus f mu alpha f nu alpha plus 1/4 G mu nu, F mu nu, F mu nu. This was this Belinfante. If we do the same procedure for the scale current, we can make the scale current just the, we can make the scale current just the T mu nu, sorry, I need that uppers, T mu nu X nu. In this case, the divergence of the scale current is T mu mu, is just the trace. And if you go back up here, T mu mu is minus F mu alpha F mu alpha plus 4 for the trace of G mu nu over 4 F mu alpha and they should be, or lambda, this should be, have been lambda sigma. The symmetric energy momentum tensor is traceless in 4 dimensions, and so we get the trace of the energy momentum tensor equal to 0. Okay, so this is a slight diversion here because the scale current in general is not just the trace of the energy momentum tensor, but if you do the improvement, the usual statement that you see, scale symmetry implies that the energy momentum tensor is traceless. This works, this improvement works for photons and for fermions. And it works for scalars if that conformal factor was 1/6. Okay, so remember I had this improvement where there's this conformal coupling. When that equals 1/6, the scalars is also traceless. Long-winded digression. That's not what I was actually the point of the class, but I did want to talk about this. This is actually important for, well, I'll give the example later on. The trace of the energy momentum tensor can measure the mass of particles. So a traceless energy momentum tensor implies that all the particles are massless. Okay. So I'm going to do 4 pathways through this. I'm going to talk about 4 different pathways. The first pathway is path integrals. And at the end of the last class, I set up a test that involved making a transformation. I'm going to go through it for this case, but the test involved, did the integral over phi equal the integral over phi prime, where this is some transformed okay. So The first thing I want to talk about is this transformation here, whether when you transform the fields, whether the Jacobian is 1 or is not. And this was the test that was suggested by Fujikawa. And it in some ways manifests the anomalies in its purest form. Basically, the Lagrangian can be invariant, but the path integral can still be not invariant. That happens when the Jacobian is not equal to 1, or not equal to just a plain old number. Okay, so the logic here is neither tells us the Lagrangian is invariant. Fujikawa tells us the path integral isn't. So therefore, we have an anomalous relation. Okay, the first thing I'm going to do is I'm going to do the Jacobian, because that's where all the action is. And then I'll come back, I'll go back to that test that I did last time to calculate what the trace of the energy momentum tensor actually is. Okay? Or what the anomaly is. Okay? So let's start. The rescaling that I'm going to do is I'm going to look at a fermion field psi of x, and I'm going to rescale it, and the particular rescaling I'm going to choose is minus alpha of x over 2 psi prime of x. And so just look at that part of the rescaling. Okay. So Bohr is going to rescale the same way. And so when I have a path integral, I'm going to have integral d psi bar. I'm going to try changing that over to d psi prime, d psi bar prime. And the Jacobian is the determinant of that change of variables, determinant e to the minus alpha of x. So there's actually 2 of them. They're the same. And so I've just put e to the minus alpha of x to the 1. Okay, so this is the standard determinant that you get from changing variables. The determinant is over space-time. These guys are 4x4 matrices, so it will be over Dirac indices. And if I'm doing, actually the example I have worked out actually is QCD, so it will be over color variables also in QCD. Okay, there be no color in QED. Okay. So normally you would just say that that's a constant. We wouldn't bother with it. We'd just throw it away. But Fujikawa's insight was that to make this well-defined, you have to regularize it somehow. And he proposed some gauge invariant regularization. So Fujikawa basically said, if this is so well defined, I can take that determinant and write this as the determinant of, well, let's make it exponential, then alpha of x minus alpha of x e to the minus d slash over m quantity squared. Okay. I'm going to take m goes to infinity at the end. And so by taking the limit m goes to infinity, I'm cutting out the highest frequency stuff, but we'll end up finding out that there's a leftover factor of that's of fields that's left over. Okay. This is again, a pretty formal object, but let's just plug away at it like we normally do. We would write this as e to the trace log of this exponential, which is then e. Well, the trace will go over space-time indices, Dirac indices, and color indices. So let's just take out the space-time indices, d4x. I've got the trace left over. This trace left over is over Dirac and color. And I've got x, alpha of x, e to the minus d slash over m, quantity squared, x. Okay, so this is now, this trace is over Dirac and color. So I've got the space-time indices out. Okay. Now, at this stage, we pull out our heat kernel. Heat kernel techniques. Remember the heat kernel, h of x and tau was x e to the minus tau times some differential operator, x. Okay. And there's the minus sign there. So this quantity that we have to evaluate is really just the heat kernel with tau being 1 over m squared and the differential operator being d slash d slash. Okay. And we've evaluated this, and so all we have to do, we've evaluated this for the form d mu plus sigma. And so if I can put d slash in the form d mu plus sigma, I'm done. Okay. Yeah, alpha is a function of x anyhow, so it's included. It's up here. At this stage, I have to. I can just pull the alpha outside the x. Okay. Okay. So the calculational goal then becomes to put d slash in that form, and then we just look up the answer and we're done. Okay. With tau equals 1 over m squared. Okay. Well, d slash is little d slash. Well, actually, let's make one extra step. You can see it better than d mu plus I g lambda a over 2 a slash d slash plus I g lambda. Let's make it b a b slash over 2. Okay, so we've got two gamma matrices next to each other, and I'm going to always use the identity gamma mu gamma nu can be written as 1/2 gamma mu, the symmetric combination, plus 1/2 the antisymmetric combination. This first piece here is just G mu nu. So if I have a symmetric combination like I write d slash d slash, I just get the G mu nu piece. The antisymmetric combination is related to sigma mu nu. It's a 2 by, it's a antisymmetric combination just called sigma mu nu. And so we get a set of pieces here. The symmetric combination here, when you multiply these together, turns into it's basically d mu plus I g lambda a over 2 a mu a d mu plus I g lambda b over 2 a b mu. Okay, so the symmetric combination just gives you those terms. And then there's a piece with its I as its 1/2 sigma mu nu is again. And the antisymmetric piece starts off with derivatives acting on A, so d mu A nu minus d nu A mu. So that's the derivatives acting on A. And the second piece there is G F A. So this is A B C A B A C mu nu times G lambda A over 2. Okay, so I've collected, you can see the antisymmetric combinations coming out, and then there's one with 2 A's that I've done a little algebra on. Okay, this is the d mu piece. This is the sigma piece. And so I've put this operator into the form d mu plus sigma. This guy here, I'm sorry. F, that's right. This is the field strength tensor. F. Sorry. I'm sorry. I'm sorry. FAB, Okay. Yeah. Okay. I didn't say that. This is the field. This when I have lambda A, lambda B is 2I FABC, lambda C. It's the SU3 structure constants. And I use that. Clearly I'm skipping a couple steps here just to save time. But I have lambda A times lambda B here. I've used that identity on this antisymmetric piece here, because I get the antisymmetric piece of these two lambda dot A, lambda dot A pieces. That's my structure constant. Okay, and this guy here, the overall thing that comes out here is the field strength tensor F A mu nu for the Yang-Mills field. Okay, so it comes with the derivatives and this quadratic piece. Okay. All right. Okay. At this stage, we're essentially done. The work we put in before tells us that the heat kernel coefficient is the following. I get h of x and tau. Tau is going to be 1 over m squared. What we had before, I had I e to the minus m squared tau, but here m squared is 0 in this case. There is no mass term. I get over 4 pi to the d over 2. D is going to be taken to be 4. 1 over tau to the d over 2. So this guy's going to turn into an m to the 4th in the numerator. And then I had 1 minus tau sigma plus tau squared over tau squared, yeah, so tau squared. And what was sitting in here was 1/2 d mu comma d nu, d mu comma d nu, plus 1/2 sigma squared, and then there was a piece that's going to contribute nothing, which was d mu commuted with d mu commuted with sigma. Okay. So at this stage, I can evaluate things. I'm going to have to take the trace on this. I don't know. I've got. Let me not work out all the steps. I have all the steps here. The d mu, d nu, d mu, d nu gives me something that's proportional to fa mu nu, fa mu nu. When I take the trace, the sigma squared piece also is when I take the trace is fa mu nu, fa mu nu, and so you just have to add those two together in some particular combination. The answer is let's write it down here. Trace x e to the minus d slash over m squared x. It's 3i m to the 4th over 4 pi squared. That's from the one piece. Okay, because tau was 1 over m squared. I have 1 over tau to the d over 2, so it's m to the 4th upstairs. The trace of sigma was 0. It's the sigma mu nu, and then trace of these guys, that guy is non-zero, and the trace of that one is 0. Okay, so I get that guy, and then plus I g squared over 48 pi squared fa mu nu, fa mu nu. Okay. So the first piece is just a plain old constant. that we will end up throwing away, that wouldn't bother us so much. But the second piece involves the field strength tensors, and that's going to give us our trace relation. Okay. So the Jacobian wasn't one. So this Jacobian is e to the I integral d for d4x alpha of x times this 3 to the fourth over 4 pi squared plus g squared over 48 pi squared f squared. Okay. All right, so there's a Jacobian, and that's the hard work. And now let's go back to the test.